Hello. All right, you made it through. You got through this what was a fairly long assignment. Congratulations. But now let me just explain and hopefully tie together some of this information and just review some of the answers with you to help try and make sense of some of this. All right. So, you started with this first part right here. What I was wanting this to do was I was wanting this to try and hopefully, here, let me make my face a little bit smaller for you. So what I was showing this for is that I wanted you to see visually what you heard in the Doppler effect demonstration. When I was moving my phone back and forth, this is basically what was happening. When the phone was moving towards you, the waves in front of the phone were getting compressed. And so you heard a different pitch. You heard a higher pitch. When the phone was moving away from you, then the wavelengths became longer, so you heard a lower pitch. So hopefully your answers reflect that down in here, where over and over again, I wanted you to get this idea in your mind that when objects move towards you, the wavelengths become shorter. When objects move away from you, the wavelengths become longer. The reason for that, just not to go too much over some of your heads, is just that as an object moves towards you, it's giving out wavelengths and it's kind of catching up with them, and so it creates this little compression in the front. However, if it's moving away from you, then the wavelengths get left behind a little bit, so they become longer, right? All right, so that's the first section. Then this next section right here, what I wanted you to see was what I again just reviewed with you was just that idea of wavelengths becoming either longer or shorter if objects are moving towards you or away from you. But then I wanted to remind you about this little idea, that the wavelength of light is really what determines the color that we see. You are seeing different colors because that's the wavelength that you actually are seeing coming off of that object. If you see a red shirt, it's because it's giving off this wavelength. If you see a blue shirt, it's because it's giving off this wavelength, right? So on here, to go from violet to red, all you have to do is just make the wavelength longer. Or if I go from green and if I push them closer together, that green is going to appear more blue or purple. Or if I take that same green and I stretch the wavelength, that same green is now going to appear yellow or orange. All right? Then we reviewed this idea of, okay, now we have all the light spectrums from different elements. We know that if a star is made out of a certain element, and if we look at it with a spectrometer, then we could actually see this pattern of lines, and we can know, oh, that star is burning a lot of hydrogen, so it's mostly made out of hydrogen, because this is the pattern of lines we see with the spectrometer. Or, oh, that star actually has neon in it, because we see the pattern of lines for neon come up. Okay? Each one of these lines, again, is just based off of a certain wavelength that's being given off. Now, this is where we tied everything together. And let me even show you here in the simulation itself. We have a star, and let's say that star and us, neither one of us are moving. If I look at that star, the spectrum, and I don't know what element this is, but it's some element. It matches up with one that we know here on Earth, so we know what element it is. But as we look at this star, if it's not moving, that spectrum will line up with what it should look like here on Earth. But if this star starts to move in any way, what's going to happen to the wavelength? If it starts moving away, it's going to stretch the wavelengths further apart. If it starts moving towards us, then the wavelength is going to be compressed. They're going to get closer together. So if it starts moving towards us, watch what happens to the spectrum. The faster and faster I make it move away from us, the more it's going to stretch out those wavelengths. And if I make wavelengths longer, what side of this spectrum, blue, purple, or red, has longer wavelengths? Reds. So the whole spectrum is going to shift towards the red because all of the wavelengths are being stretched longer. However, what if I make the star move towards me? Now I'm going to be making the wavelengths shorter, which means we are going to see this spectrum shift the other way towards the blue. I'm going to make this very big. This is how we can tell how other stars are moving anywhere in the universe. By looking at any star anywhere, and by looking at its spectrum pattern, and is that spectrum pattern, it's showing a pattern for this element, but it's shifted. It's the same pattern, but it's moved one way or the other. By looking at that pattern and seeing how much it shifted, we can tell how other stars are moving. Not only that, depending on how much it shifted, we can tell how fast other stars are moving, either away from us or towards us. So what is the point of all of this? Here's what it comes down to. There was a famous scientist by the name of Edwin Hubble. If that name sounds familiar, it's because maybe you've heard of the Hubble Space Telescope. It's named after him for a good reason. Edwin Hubble, when they really first started analyzing stars and looking at their spectrums, he was looking at the spectrums coming off of stars in faraway distant galaxies. And one of the discoveries he made is that no matter where he looked, with very, 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 very few exceptions, no matter where he looked in our universe, every single star and galaxy, or every other galaxy outside of us, was moving away from us. All of them were red shifted. All of their spectrums were shifted towards the red side. Red shift means that the spectrums were longer wavelengths, meaning that objects were moving away. He found evidence that everything in the universe was moving away from us. So, if everything is moving away from us, then if we go back in time a day, then that means everything yesterday was closer together. What if we go back a year? Everything was closer together. What about 10,000 years? Closer together. If you run the clock back over and over and over and over, you eventually arrive at just the logical idea that if everything is constantly moving apart from each other, all the galaxies, that is, are constantly moving apart from each other, then that means that at one point, everything was once actually together. This was one of the first big pieces of evidence for something called the Big Bang. This idea that at one time, everything in our universe used to be in one single spot, but that ever since that event has then been moving away and is continuing to move out and expand. So, hope that's mind-bendy enough for you. Okay, thanks friends. Later.